Titan is the largest moon of Saturn. It is the only natural satellite known to have a dense atmosphere, and the only object other than Earth where clear evidence of stable bodies of surface liquid has been found. Titan is the sixth ellipsoidal moon from Saturn. Frequently described as a planet-like moon, Titan's diameter is 50% larger than Earth's natural satellite, the Moon, and it is 80% more massive. It is the second largest moon in the Solar System, after Jupiter's moon Ganymede, and is larger by volume than the smallest planet, Mercury, although only 40% is massive. Discovered in 1655 by the Dutch astronomer Christian Huygens, Titan was the first known moon of Saturn, and the fifth known satellite of another planet. Titan is primarily composed of water, ice and rocky material, much as with Venus before the space age. The dense opaque atmosphere prevented understanding of Titan's surface until new information accumulated when the Cassini-Huygens mission arrived in 2004, including the discovery of liquid hydrocarbon lakes in Titan's polar regions. The geologically young surface is generally smooth, with few impact craters, although mountains and several possible cryovolcanoes have been found. The atmosphere of Titan is largely nitrogen. Minor components lead to the formation of methane, ethane clouds and nitrogen-rich organic smog. The climate, including wind and rain, creates surface features similar to those of Earth, such as dunes, rivers, lakes, seas, and deltas, and is dominated by seasonal weather patterns as on Earth. With its liquids and robust nitrogen atmosphere, Titan's methane cycle is analogous to Earth's water cycle, although at a much lower temperature. History: Titan was discovered on March 25, 1655 by the Dutch astronomer Christian Huygens. Huygens was inspired by Galileo's discovery of Jupiter's four largest moons in 1610 and his improvements in telescope technology. Christian, with the help of his brother Constantin Huygens Jr., began building telescopes around 1650 and discovered the first observed moon orbiting Saturn with one of the telescopes they built. He named it simply Saturn I Lunar, publishing in the 1655 tractate Saturn I Lunar Observation Over. After Giovanni Domenico Cassini published his discoveries of four more moons of Saturn between 1673 and 1686, astronomers fell into the habit of referring to these and Titan as Saturn I through V. Other early epithets for Titan include Saturn's ordinary satellite. Titan is officially numbered Saturn V because after the 1789 discoveries the numbering scheme was frozen to avoid causing any more confusion. Numerous small moons have been discovered closer to Saturn since then. The name Titan, and the names of all 7 satellites of Saturn then known, came from John Herschel in his 1847 publication Results of Astronomical Observations Made at the Cape of Good Hope. He suggested the names of the mythological Titans, brothers and sisters of Cronus, the Greek Saturn. In Greek mythology, the Titans were a race of powerful deities, descendants of Gaia and Uranus, that ruled during the legendary Golden Age. Orbit and rotation: Titan orbits Saturn once every 15 days and 22 hours. Like the Moon and many of the satellites of the giant planets, its rotational period is identical to its orbital period. Titan is thus tidally locked in synchronous rotation with Saturn, and permanently shows one face to the planet. Because of this, there is a sub-Saturnian point on its surface, from which the planet would always appear to hang directly overhead. Longitudes on Titan are measured westward, starting from the meridian passing through this point. Its orbital eccentricity is 0.0288, and the orbital plane is inclined 0.348 degrees relative to the Saturnian equator. Viewed from Earth, Titan reaches an angular distance of about 20 Saturn radii from Saturn and subtems of disk 0.8 arcseconds in diameter. The small, irregularly shaped satellite Hyperion is locked in a 3 to 4 orbital resonance with Titan. A slow and smooth evolution of the resonance, in which Hyperion would have migrated from a chaotic orbit, is considered unlikely, based on models. Hyperion probably formed in a stable orbital island, whereas the massive Titan absorbed or ejected bodies that made close approaches. Bulk characteristics. Titan is 5,151 kilometers in diameter, compared to 4,879 kilometers for the planet Mercury, 3,474 kilometers for the Moon, and 12,742 kilometers for Earth. Before the arrival of Voyager 1 in 1980, Titan was thought to be slightly larger than Ganymede, and thus the largest moon in the Solar System. This was an overestimation caused by Titan's dense, opaque atmosphere, which extends many kilometers above its surface and increases its apparent diameter. Titan's diameter and mass are similar to those of the Jovian moons Ganymede and Callisto. Based on its bulk density of 1.88 grams per cc, Titan's bulk composition is half water ice and half rocky material. Though similar in composition to Dione and Enceladus, it is denser due to gravitational compression. Titan is likely differentiated into several layers with a 3,400 km rocky center surrounded by several layers composed of different crystal forms of ice. Its interior may still be hot and there may be a liquid layer consisting of a magma composed of water and ammonia between the ice crust and deeper ice layers made of high-pressure forms of ice. The presence of ammonia allows water to remain liquid even at a temperature as low as 176 K. Evidence for such an ocean was uncovered by the Cassini probe in the form of natural extremely low-frequency radio waves in Titan's atmosphere. Titan's surface is thought to be a poor reflector of extremely low-frequency radio waves, so they may instead be reflecting off the liquid ice boundary of a subsurface ocean. Surface features were observed by the Cassini spacecraft to systematically shift by up to 30 kilometers between October 2005 and May 2007, which suggests that the crust is decoupled from the interior, and provides additional evidence for an interior liquid layer. Further supporting evidence for a liquid layer and decoupled ice shell comes from the way the gravity field varies as Titan orbits Saturn. Comparison of the gravity field with the radar-based topography observations also suggests that the ice shell may be substantially rigid. Formation. The moons of Jupiter and Saturn are thought to have formed through co-accretion, a similar process to that believed to have formed the planets in the Solar System. As the young gas giants formed, they were surrounded by disks of material that gradually coalesced into moons. However, whereas Jupiter possesses 4 large satellites in highly regular, planet-like orbits, Titan overwhelmingly dominates Saturn's system and possesses a high orbital eccentricity not immediately explained by co-accretion alone. A proposed model for the formation of Titan is that Saturn's system began with a group of moons similar to Jupiter's Galilean satellites, but that they were disrupted by a series of giant impacts, which would go on to form Titan. Saturn's mid-sized moons, such as Iapetus and Rhea, were formed from the debris of these collisions. Such a violent beginning would also explain Titan's orbital eccentricity. In 2014, analysis of Titan's atmospheric nitrogen suggested that it has possibly been sourced from material similar to that found in the Oort cloud and not from sources present during co-accretion of materials around Saturn. Atmosphere. Titan is the only known moon with a significant atmosphere, and its atmosphere is the only nitrogen-rich, dense atmosphere in the Solar System aside from Earth's. Observations of it made in 2004 by Cassini suggest that Titan is a superrotator, like Venus, with an atmosphere that rotates much faster than its surface. Observations from the Voyager space probes have shown that Titan's atmosphere is denser than Earth's, with a surface pressure about 1.45 atmospheres. It is also about 1.19 times as massive as Earth's overall, or about 7.3 times more massive on a per-surface area basis. It supports opaque haze layers that block most visible light from the Sun and other sources and renders Titan's surface features obscure. Titan's lower gravity means that its atmosphere is far more extended than Earth's. The atmosphere of Titan is opaque at many wavelengths, and a complete reflectance spectrum of the surface is impossible to acquire from orbit. It was not until the arrival of the Cassini-Huygens spacecraft in 2004 that the first direct images of Titan's surface were obtained. Titan's atmospheric composition in the stratosphere is 98.4% nitrogen, with the remaining 1.6% composed mostly of methane and hydrogen. There are trace amounts of other hydrocarbons, such as ethane, diacetylene, methylacetylene, acetylene and propane, and of other gases, such as cyanoacetylene, hydrogen cyanide, carbon dioxide, carbon monoxide, cyanogen, argon and helium. The hydrocarbons are thought to form in Titan's upper atmosphere in reactions resulting from the breakup of methane by the Sun's ultraviolet light, producing a thick orange smog. Titan spends 95% of its time within Saturn's magnetosphere, which may help shield it from the solar wind. Energy from the Sun should have converted all traces of methane in Titan's atmosphere into more complex hydrocarbons within 50 million years, a short time compared to the age of the Solar System. This suggests that methane must be replenished by a reservoir on or within Titan itself. The ultimate origin of the methane in its atmosphere may be its interior, released via eruptions from cryovolcanoes. On April 3, 2013, NASA reported that complex organic chemicals could arise on Titan, based on studies simulating the atmosphere of Titan. On June 6, 2013, scientists at the IAA-CSIC reported the detection of polycyclic aromatic hydrocarbons in the upper atmosphere of Titan. On September 30, 2013, propene was detected in the atmosphere of Titan by NASA's Cassini spacecraft, using its composite infrared spectrometer. This is the first time propene has been found on any moon or planet other than Earth, and is the first chemical found by the CIRS. The detection of propene fills a mysterious gap in observations that date back to NASA's Voyager 1 spacecraft's first close flyby of Titan in 1980, during which it was discovered that many of the gases that make up Titan's hazy brown-colored haze were hydrocarbons, theoretically formed via the recombination of radicals created by the Sun's ultraviolet photolysis of methane. On October 24, 2014, methane was found in polar clouds on Titan. Climate. Titan's surface temperature is about 94 K. At this temperature, water ice has an extremely low vapor pressure, so the little water vapor present appears limited to the stratosphere. Titan receives about 1% as much sunlight as Earth. Atmospheric methane creates a greenhouse effect on Titan's surface, without which Titan would be far colder. Conversely, haze in Titan's atmosphere contributes to an anti-greenhouse effect by reflecting sunlight back into space, cancelling a portion of the greenhouse effect and making its surface significantly colder than its upper atmosphere. Titan's clouds, probably composed of methane, ethane or other simple organics, are scattered and variable, punctuating the overall haze. The findings of the Huygens probe indicate that Titan's atmosphere periodically rains liquid methane and other organic compounds onto its surface. Clouds typically cover 1% of Titan's disk, though outburst events have been observed in which the cloud cover rapidly expands to as much as 8%. One hypothesis asserts that the southern clouds are formed when heightened levels of sunlight during the southern summer generate uplift in the atmosphere, resulting in convection. This explanation is complicated by the fact that cloud formation has been observed not only after the southern summer solstice but also during mid-spring. Increased methane humidity at the South Pole possibly contributes to the rapid increases in cloud size. It was summer in Titan's southern hemisphere until 2010, when Saturn's orbit, which governs Titan's motion, moved Titan's northern hemisphere into the sunlight. When the seasons switch, it is expected that ethane will begin to condense over the South Pole.